Second here. Okay, so today I'll be speaking about a review of Softcore fourth processors. I'm building so we're talking about FPGAs. We're talking about the design of processors that explicitly, have fourth words for instructions and then implement fourth languages on top of it. There's no hardcore processors, but we can do a lot of great stuff on these FPGAs, and they're getting much more dense. This is the master's. I returned to graduate school. It's free for here in Poland if you speak Polish. So I returned to graduate school and learned an awful lot. Okay, so I'm going to skip hold on a second. Let me see how to change slides here. Okay, so I'm going to skip the part about what is fourth. We all know. I'm sure you know about the RTX 2000, which recently landed on a comet as part of the Philae lander, and Okay, so why are people interested in this? Well, usually the electrical engineers want to build some large application, sort of a sea of gates to do something useful, and what they need is some high-level logic, what they call a system within a chip. It's a small soft-core CPU within a chip, but specifically where the CPU is neither the purpose of the chip nor the main application within it, says Dan Gisselquist of Zip CPU. Don't confuse Zip CPU with the very famous Z CPU, which we'll speak about in a moment. So why would you want a fourth stack machine in your FPGA? Well, the Propeller Parallax is a machine with 8 32-bit register machines, but it also includes fourth in ROM. And the author, Peter Jakatsky, said Tacos fourth in ROM is implemented primarily for debugging hardware, testing out what-ifs. So you just use a shell to enter into your device, and you can do some interpreted commands and find out what's working and what isn't. So it's very convenient for that, for debugging also. But really, if you think about the comparison between C and stack machines running fourth, the latter can be much more efficient. In C, you have a single address space, which includes your data, your instructions, and your stack. And so if you have single port memory, meaning that only one item can access the memory at the same time, there's contention, and so it slows you down. On the other hand, if you have something like fourth, certainly on the very well-known J1 processor, the data stack and return stack are outside. The instructions can either be in the same memory space or they can be outside. The microcore has them outside, whereas on the left of the C machine just has the registers outside. So you get much less contention for memory on a stack machine. You can get less. Small memory, James Bowman implemented on a 32-bit microblaze. He had 16,000 bytes of code. On the J1, he just had 6,000 bytes. And so what happens then is he was able to add in a lot more functionality, and so he was building FPGAs for video processing. So he could do a lot more functionality for his end users because it took up less memory. Smaller devices, the smallest device that runs C language is called the ZPU. It weighs in at 442 LUTs, whereas the J1 weighs in at either 160 LUTs, or if you only have a 1-bit shifter, at 80 LUTs. LUTs is a measure of size on FPGAs, lookup tables. Why else would you want a fourth stack machine? Well, if you look at the GNU C compiler, it has 16 million lines of code, really hard to innovate. You have fourth stack machine, simple, understandable, modifiable. The J1 is less than 200 lines of code. You can do whatever you need to. The imagination is free. Okay, so when I was looking, there are a large number of these machines. You can see them listed on the left, go down. We'll review all of them. But what I'm going to do now is I'm just going to review what the constraints are. And at the end, we'll talk about each one and how they fit into this chart. And what I realized, these machines are all very different, and it took me a while to realize they're all subject to different constraints. And so based on what constraints, you end up with a different design of the CPU. So the J1 was in a commercial product. He really wanted to minimize the cost. Other ones like the microcore were limited by RAM, particularly 8-bit wide RAM and probably single port memory. On the low end ICE40 devices, I'm also facing single port memory problems. J1 was concerned with LUTs. He really wanted the maximum frequency. Some people want memory efficiency, and so they want to compress the instructions down. Others want the best application speed. What the microcore does is every time he has something that's too slow, he moves it into instructions. So he's got like 86 instructions, but then all of his applications run really quickly. So he's concerned more about application speed, even though the clock speed is lower. Portability, the Ting E4th ran on tons of different platforms, and so he really wanted a fourth that was very portable. A lot of us would like to minimize the work by reusing something. The J1SC does very flexible designs. And the one thing I couldn't put on this slide is sort of what's trendy. So clearly, a lot of people are using the J1. It's trendy. It's good to talk about it. So that's another issue, might be another constraint. Okay, so where do you want to start if you're interested in these things? Well, Dr. Ting's EP 16, 24, 32, and 64 are a good place. He had beautiful documentation in VHDL. It's a good place to learn about it. E4th has installed base and is very widely ported. It has 27 instructions. But sadly, the EP32 never had any traction. Why not? Well, I think that the electrical engineers really care about the LUTs, how much space it takes up. And so they ended up all jumping on the J1. And because you need to be an electrical engineer to do these things, the J1 took off. Another one that had some commercial success was the B16, much like the Dr. Ting's cores. It also had 5-bit instructions, which mean in a 16-bit word, you could pack 3 of them in. So you get much more memory efficiency. Both of those were concerned with memory efficiency. I really like the microcore with lots of instructions. He does some very complex applications with it. It's got not only 82 instructions, it's got coroutines, variable data width, variable math width, runs on a ton of different platforms. So quite an interesting platform to choose if you're building something. But of course, the one that everybody loves is the J1 A and B. It's small, it's fast, it's popular, it's brilliant. It's very understandable, but it's limited. For example, it doesn't have interrupts, doesn't have I/O ports. So there's 16 J1 operations. If you're a fourth developer, top of stack, sort of duplicate the top of stack, copy over the next of stack, add them, and okay, I won't go through all of these. So, but those are all the operations it has. And if you look at the fourth, at the Verilog, I'm not sure how many people here read Verilog, but basically, based on what the instruction is, you get your different fourth instructions. So based on what the 16 bits are of the instruction, it'll execute in different fourth instructions, and it'll set the top of stack next in stack appropriately. If you don't like Verilog, there's a similar identical processor in VHDL called the H2 processor. It has interrupts. It also has a SEEP simulator with the whole VGA demo and stuff. So also has hold variables, larger stack depth. So there are lots of different flavors of these J1s. But really, if you're interested in using it, what you want to do is use the MeCrisp Ice. They've added in ports and tick counter, constant folding, inlining, tail call optimizations, SPI access with flash. It runs on boot, very fast 2-cycle interrupts. You can get more instructions if you want. So these are sort of all the things that the J1 took out, he put back in. And it runs on lots of different platforms. So I'm not going to go into the detail here. A couple of the platforms, I think I was reading the source code. It runs on about 10 different platforms now. And there's even an unofficial version on the Arduino, which is the device I'm working on. This is based on the very inexpensive, this is only like a $35 board, so everybody can get one. It's like no big deal, right? It's based on the inexpensive Lattice Ultra Plus ICE 40 up 5K FPGA. It's got 5.3K LUTs, 1 megabyte of single port RAM, 120 kilobytes of double port RAM. And of course, that's where the problem lies, because the J1 expects double port. So you have to do some work to use the single port. It's not that difficult. And then it's got all the other stuff that you need on a board that you can do stuff with. The other really interesting version is the J1SC. This is in an implementation of the J1 CPU in Scala using Spinal HDL, a high-level language in Java. And the claim to fame of spinal HDL is the VEX RISC-V, which won the first prize at the RISC-V Summit. If you click on the links on the underlined title, takes you to all the links for all these things. But basically, because it used a high-level design language, it was so flexible. You had so many options. You could configure the chip any way you wanted, things that are really very difficult to do in native Verilog. So a J1 in spinal HDL is a very interesting thing to start with. And of course, we all love the Core 1. He's really focused on artificial intelligence, and he's got lots of instructions, which I like. It's got pauses, which are really important for these things. No cross compiler needed. And very, very much sort of in the electrical engineering concept of embedding in a larger FPGA project, and a huge, huge following on Facebook. So if you're interested in these things, it's a really rich community. There are lots of simulators. You can simulate in Verilator, which is a Verilog simulator. The Swap4, there are two different C simulators. There's the Python simulator, there's a Java simulator, and there's a G4 simulator for the microcore. So lots and lots of tools to choose. And of course, you need some terminal on your desktop to talk with. So eforth.com connects to a lot of different, not only FPGAs, but also various Forth running on different microcontrollers. And you can see like all the different Forths that it connects to. So Forth is a very rich, dynamic community, diverse. Okay, so I studied this in order to figure out what I should do for my master's thesis. And basically, I think the really low cost boards are really interesting to place to be. And so the first one I want to release is the Hana 1. And so I need to port the J1 to single port memory. And really what you need to do is give it priority memory so that you can either have, if it's fetching an instruction, which the J1 does every clock cycle, then it does that. But if it's reading or writing to memory, which maybe it does 10% of the time, then that gets priority in the instruction and the whole device pauses. And so these devices have 8,000 16-bit words, and that's how much RAM they have. I think there's a typo in that. They have a, that's how much dual port RAM they have as opposed to single port RAM. Then the next thing I want to do is I want to do eight of these cores. And so Parallax Propeller has 8 cores for real-time control, each with not much memory. And so here we could have 4 larger cores and 4 smaller cores with that much memory. And then once you start having multiple cores working together, you can do interesting things like Fourier transforms shared across. So you get like an 8 times speed up compared to a single one. And so then that's operating at close to 400 megahertz, which is faster than most of the microcontrollers. And then once you're doing that, you can do hearing aids, which one of the people here actually asked for. And so there's actually, if you click on the link, there's a whole group called Computational Audiology, and they've actually built a little programmable hearing aid, and they've run into the limits of performance. And so they're considering doing a system on a chip, which is a chip with both a microprocessor to run C, plus it has an FPGA to do all those additional algorithms. And of course, stereo audio is 16 bits. And so ICE40 is a low power FPGA. It's got 16-bit multipliers, and it's got 16-bit memory. And a lot of solder Forths actually need hearing aids and be very happy to be able to program on. So interesting device. Here you can see when you break it open, what's there. And basically what you can do is you can add all kinds of things in software: low pass filters, band pass filters, high pass filters, FFTs, frequency shifters, sound localization. And then different people can play with these different algorithms and put them together and find out what works best for their particular hearing situation. So that's would be the Hana 8. You could do that, but also the same company that sells the Arduino also has the Pico Ice, and there it has an RP2040, and that gives you 2 more cores with 256K bits of RAM. And Zepto Forth, it runs Zepto Forth, MeCrisp Forth, no Forth. So you get a choice. Zepto Forth supports communicating sequential processes, much like the transputer. So that looks really interesting, and it actually boots on the board. So then you get your FPGA running your custom algorithms. You also get 2 more cores on the RP. So all for $35. Great. Okay, so what are the reactions when James said, where can I buy this? Another gentleman said he actually bought the board already. He's like, okay, when are you going to ship it? Currently, 2 weeks after I get the boards, and I'm just waiting for the boards to arrive in the mail. It will be the first release. There'll be a series of releases with more functionality. And then, of course, these are just tiny things, but imagine a large number of these. Green Arrays had 144 of them, but I think can go up to 400 of them, enough for have a complete image in memory. Or even on the smaller devices, you just do an array of them as the image passes. You can do filtering on the image as it goes by. So you can imagine doing all kinds of things with lots of these small fourth processors. It's interesting. This is actually a 200 by 200 pixel image. If it was 24 bits deep, that would be 1 megabit. And that's how much memory is on the inexpensive board I'm using, which is, why we're not doing vision on the low end boards. Plus you get flooded with the cameras flood you with data. So that's another issue. Okay, so back to our constraints. What are we looking at? Well, the J1 was really concerned about minimizing costs, minimizing the LUTs, maximizing the speed. Then he did a brilliant job, and all the electrical engineers love it. MeCrisp, those are important, but he really wanted to get a lot more work done. So he put all that stuff back in that's needed. Microcore has a ton of, has the 82 applications, much like the Core 1 has. Maybe Core 1 has 71, something like that. So that, I like that approach. EP16 and the B16 and also I were very focused on how much memory there is. One of the things I want to do is instruction prefetch. So the MeCrisp does instruction inlining, but then that consumes a lot of memory. Whereas if you do instruction prefetch, it effectively is inlining because you don't have to wait for when you're doing a jump because you've already prefetched that instruction. So that gives you a lot more memory. And then what else do we have here? Okay, so the idea is that the key lesson here is that all of these cores look different, but they're all driven by different constraints. And once you understand what the constraints are, then you understand why they've made those design choices. Okay, so you can reach me, Christopher Lozinski, at fourth.pythonlinks.info, Lozinski at pythonlinks.info, or mastodon.social and Twitter are the best places. Any questions?
Can you go back to your chart? The previous slide.
Going back to my chart. There we go.
So on the Core 1, portability and max design flexibility would be checked.
Okay, let me hold on a second. Hold on a sec.
Those were goals in our design.
Yeah, makes a lot of sense. Core 1, portability. I'm just making notes for later.
Yeah, that's fine.
And which one?
Portability and max design flexibility were two main.
Yeah, exactly. I'm sorry I missed that one. That one I knew about.
No worries.
That's why I'm doing this here before I do it for a big group. Thank you. I got that.
I do have a question.
Go ahead.
What compilers have you found that compile down to fourth and take advantage of fourth as a embedded softcore?
Right. So there are three versions. Let's see if I can find this here again. MeCrisp is one version that runs on softcores, and that's sort of the mainstream one. The original one was J1, had swap fourth. So J1 had swap fourth, and that's used a little bit by a couple of people, but the MeCrisp one is the biggest one. And I think I saw another one today. Oh yeah, eFourth. I saw eFourth, Ting's eFourth, which is very portable. There's also, if you look on eFourth and J1, you'll also find that one. Great question. Which force to use? So I'm making that note too. So those three, swap fourth, MeCrisp. So actually, I recommend MeCrisp first, swap fourth, and eFourth.
I have another.
Go ahead. I love these questions. Spend as much time answering them as you want.
A long time ago, I started researching and searching for I called it the holy grail of computing, which sounds insane, but I wasn't quite sure what I was searching for, and when I found fourth, I thought, well, here's what it is, but I'm not sure what it is. And when I heard Charles Moore said, well, I'm not sure what fourth is, at least I'm in good company. So, but I found that fourth can do high-level programming almost as good as it can do low-level programming because the syntax is out of the way, and because you've got that 0-point programming where you're just handing it functions, and everything that it needs is already on the stack, and then when it's done, it puts all the results on the stack. So it's very functional environment, but it's ultra high level. But it's also, where do we spend all of our time? At the low level. But Charles Moore is the amazing, genius that started all of this. But, he handed it off to us, and we made the ANS standard out of it. But he went on to, I love your grid about how people have used fourth to optimize, because it explains why every fourth looks different. Right. And but I'm trying to focus on fourth from a high level language standpoint, because I want to, as you get higher level in your programming, I'd like to maybe possibly, leave the stack juggling behind. I'm not sure. Like I keep thinking,
goals.
I keep thinking, well, we gotta, put a scheme or a Lisp or.
Right. Well, I completely agree with you. Right.
On top.
So there's a difference between the logic and the stack juggling, and much like the register machine people have compilers, we should be able to have some slightly more abstract definition and have like a fourth compiler figure out exactly how to juggle the stacks for us. So I completely agree with you on that one.
Well,
my favorite choice is Dylan, because it's a Lisp, but it's infix. It was invented by people at Apple many years ago, and now there's a new Dylan called Open Dylan, and it's sort of Pascalish, but I want to. That's sort of as close as I could get to bridging the world of C programmers, because
I got a comment, because one of the things is.
Wait a minute, can I finish?
Yeah. Yeah, go ahead.
I think that what you put on top of fourth is really important. And I'd like to say that I think that Dylan, or something like it, would be a good thing to get people programming on top of fourth without having to go so far, because fourth is like a different universe almost to me.
Right. So I completely agree with you about the importance of high level languages, and I'm completely aware that this is a tiny fourth community that is tiny and doesn't really have much impact. So something like Dylan on top of it would be just fantastic. Do you remember? Let me show you. Let me jump to this other slide here. Wait a second, let's go and find it. Where is it? This one. So the Pico Ice actually runs two chips. One is the RP2040, and the other is this one. The RP2040 runs a whole bunch of stuff, and in particular, it runs MicroPython. So basically, as far as I'm concerned, you can develop in MicroPython and have a fourth subroutines. So you get the high level language, you get the low level language.
Chris,
awesome.
I was wondering about why you're connected with Python in some sense.
Yeah, I've been a Python developer for 20 years. Last century.
One of the links on my page with all videos and so forth is this guy who was involved in the development of Anaconda, Wang or something like that is his name, but he was presenting at a KX conference, and this talked about giving a talk to Python or to Anaconda, whatever, on discovering forth. And this his eyes just being opened up. I mean, he ended up talking to this Python crowd about forth. That's being, but the other thing, one phrase I've used is about coming from APL and K, which have evolved from notation for applied mathematics. I mean, that's where Iverson came from. And I jumped from Fortran and some Algol back in the mid-70s when I was having to learn multidimensional geometry and so forth. They got APL on the CDC 6600, and okay, forget that Pascal was coming in, and they had C and so forth, hadn't really gotten there. But geez, I jumped to the math because all I was interested in, but not because the generalization of math that you see in the way that I do accounting, fundamentally lists of various types, characters, whatever. But there's simply, there's no higher level languages than APL in terms of, oh boy, that gets into the definition of higher level. Because from somebody who's coming from a business perspective and looking at this, the high level is what you all are talking about. all the intricacies of the various architectures and so forth. That's high level. That's high level.
So my biggest comment is thinking forth. Use forth to create a natural language, and that will be actually higher than Pascal or any other language. One of my criticisms, Bob, I hate to do this to you, but your APL is so cryptic, I can't read it.
That's it, but at the same time, I can say the same thing about the other perspective, and there's no question that it's dense. I mean, that's the nature of mathematics, and the whole notation is, and one of the things that needs to be recognized is everything you see is actually executing in forth. That's it. It just is going, and some of the complication in notation is the fact that, like, you have to specify that it's a float or an int or whatever. But and one of the things is where I've gone and my head is such that for me, I made the $sign an alias for swap. Because rarely do I go and do any. Actually, I have a whole vocabulary of picture names for all of the stack manipulations. No.
Well, you've created your own language, and now for other people to read it, they have to read your book and know that $sign means swap. That's kind of my point.
No, I don't. You just get on and you start and you write and you execute some of the sentences that are there, and then I mean, it's again, it really is an issue. And
we're not saying that your programming isn't high level language, but we're saying that it's if you're gonna involve other people, then you have to learn how to speak the same language.
Again, I mean,
So
APL
listen, I
and K
I want to get
have
back to
have
Christopher,
very.
Yeah.
I mean, there's
what he has to say about high level
yeah,
language. I appreciate you, Bob, and I appreciate your high level cozy. I really do.
I do too.
again, one of the things is you look at who's going to go and make boardroom systems. Okay, I mean that's really the ultimate mark, and for that matter, the Bank for International Settlements, they do their accounting. They're the bank that does the clearance for all the central banks in the world. Okay, they use APL. So when you're talking about competing on those sorts of things, or one of the applications of K actually is, I think it's McLaren's Formula One team uses K for doing their data monitoring. So this is absolute competitive end of programming language.
Yeah, well, it's an APL thing. So, but
Yeah, except it's executing
let's
directly.
let's stay focused on natural language
Yeah.
processing,
Oh,
because we're talking about the future computer. Look at if you're a Star Trek fan, you ask the computer in English, and that is one of my ultimate goals for the Core One project.
well,
Is we're
one
going
of
to use very. Hey,
I think
Bob, let me finish, please. Memory is cheap. To
yeah.
write out the string, and as a matter of fact, swap is too low level. Move column. You had like 3 characters or something for moving a column. Just spell it out. Move column. Move. Move column 1.
Okay, that's
So
just making more aliases, and
no, Bob.
aliases in the other
The,
direction. But
the world
yeah,
wants to talk to the computers. They
Okay.
don't want to learn to be a computer programmer.
Okay,
They want to talk to the computer.
yeah.
Let's
Actually,
let's take a break here. Let's take a break. I want to finish up with Chris and thank him for his presentation, and I want to ask him to keep us updated on his boards and applications in the future. So please consider SVFig when you have something else to present.
With pleasure.
Okay. If so, Chris, if you can unshare your screen,
Yes, one second.
that would be good.
Oh.
And don't have, there's about 5 minutes remaining, so I don't have enough time to give my presentation. So I apologize to everybody who logged in expecting to see that, but I'll be around next month. So what I'd like to do now is, basically close the formal SVFig session here, but the connection will remain because there's a lot of good discussion going on, and I don't want to stifle that. So, Brad, could you stop the recording, and then we can move into discussion.